talking about energy flow in global systems. So we're going to focus on the whole biosphere, not just say one organism. One thing that you need to know is that energy sustains life. If there were no energy, things would not be alive. And so ask yourself, what would it be like if there was no sun? And you might say, oh, well, that's no big deal. If there's no sun, I would never get sunburned. If there was no sun, yeah, it would be cold, but I'd just put on a parka, whatever. Eventually, we wouldn't have any stored energy left over. The sun is the source of basically all the energy on our planet. And so if the sun were to disappear or cease existing, we could survive for a little while. But in time, plants would stop growing because there would be nothing left for them to grow with. Once plants stopped growing, then any organism that requires a plant to survive would no longer have a food source. And so since we're pretty high up in the food chain, we won't be directly affected by this immediately. Perhaps if we're vegetarians, we will be. But we'll run out of ways to produce food very quickly if the sun were to disappear. So the sun is crucial because it is the original form of energy for basically all life on our planet. Now, what is it generated by? It's generated by the reaction that happens in the sun. Does anyone remember what it's called? It starts with an F. Yeah, it's called fusion. I just realized that asking you for an F word was probably not the smartest thing I could have done today. Anyways, it's generated by fusion in the sun. The idea is that two hydrogen atoms fuse to form one helium atom. And that's what I'm illustrating in the picture down here. This is a hydrogen. This is a hydrogen. Now you might notice that they look different. That's because they are isotopes. So I'm going to remind you of a chemistry word here. Does anyone remember what an isotope is? Oh, yes, go ahead. It has different number of neutrons. So, a little bit of final exam review. So there are isotopes of hydrogen, and if you look, that's what I'm displaying here, isotopes that have one or two. Sometimes hydrogen has no neutrons. But in this particular example, these two hydrogen atoms fuse to form helium, and some mass is lost. So here's a neutron. That mass that's lost is converted into energy according to Einstein's famous equation E equals mc squared, where E stands for energy, M stands for mass. Anyone know what C stands for? It's not a word that starts with the letter C, unfortunately. C is the speed of light. So if you look at this, think about kinetic energy, mass times speed squared. It's kind of the same thing, hey? So we're talking about mass and speed being a way that you can calculate energy. So this is where the energy is coming from. It's coming from the sun. So then we have to ask ourselves, okay, the sun did this fusion reaction. We know that we've produced some energy. How is this energy getting from the sun to us? Before I go ahead, does anyone have any questions they want to ask about this idea here, about fusion in the sun? So the energy that the sun produces is released in the form of the electromagnetic spectrum. Now, knowing all the parts of this spectrum is not our main goal, so I'm just going to give you a couple of examples to show you what I'm talking about. This would be things like X-rays, UV rays, infrared rays, visible light. So you might remember, I think it's grade 8, where you talk about this the first time or the most recent time. But those are different types of electromagnetic waves. So we're not saying that these are particles necessarily, although there's a debate about what light actually is. We're talking about waves. So there's my energy. What we're getting at is that the sun is not directly producing heat that we are feeling. The sun is way too far away for us to feel any heat that is happening in the sun because of energy conversions. Plus, we know that there's a vacuum, and I'm going to write the word void because I think I used that at some other point. What we mean is there's nothing in space, there's no particles. But because there's a vacuum or a void, heat can't be transmitted unless there are particles vibrating to transmit it. So the only way the energy gets from the sun to us is in the form of a wave. A wave doesn't need a particle to transmit it. Now, visible light is what you see. It's not the only type of energy that the sun is producing. We talked about UV rays. You can't see those. But visible light, along with the other types of radiation, reaches the outer atmosphere, and from here down to the Earth's surface, it gets reflected and absorbed by different parts of the biosphere. So I'm going to make a little list of parts of the biosphere that would do these things. The first thing that I want to mention is that reflected or scattered is basically saying the same thing. We're making it not continue along its path. Absorbed means absorbed. It got all the way to the surface, and some organism or some substance is actually absorbing the sun's energy. Now, what kind of things can reflect or scatter the sun's energy? Well, in the atmosphere, you would have things like clouds and dust that are reflecting or scattering the sun's light, meaning that they're not letting it get all the way to the surface of the Earth. Now, clouds aren't permanent, and so on a given day, the amount of solar energy that's reaching you could be different because of cloud cover. The hydrosphere could reflect the sun's energy. Now, the hydrosphere is water. Generally, water absorbs the sun's energy, but if we think about ice and snow, and we'll talk about this, things that are shiny and light-colored have the tendency to reflect. Finally, if we talk about the lithosphere, there are parts of the lithosphere that will reflect the sun's energy, not absorb it. Generally, anything that is light and shiny in texture, light-colored, shiny texture, is something that will end up reflecting instead of absorbing. And so probably without knowing, you guys know this idea already. You know that if it's really hot outside, you probably don't want to wear a black shirt because you'll be even hotter. You know that if you have a white car, it won't be quite as hot as your black car if you leave it out in the sun. Now, what kind of things absorb the sun? Well, there are parts of the atmosphere that absorb. For example, I'll mention the ozone layer. We know that it absorbs UVB radiation. There are parts of the hydrosphere. For example, an ocean. In general, liquid water is good at absorbing the sun's energy. There are parts of the lithosphere, specifically ones that are dark colored, that are not shiny in texture. They do a better job of absorbing. And finally, I want to mention in the absorbed by section living organisms. Now you might think, well, shouldn't that have been the first thing you said? Shouldn't that be the most important one? You would think so, but living organisms actually only absorb a very, very small fraction of the sun's energy. Most of it has been reflected or absorbed by something else before a producer could even absorb it. Now this picture down here is just used to illustrate that the sun's energy is not all going to stay on Earth. Some of it's going to be reflected right away. Now depending on exactly which book you look at, these numbers can vary slightly, but I want you to get the idea that it's about half and half. About half of the sun's energy is absorbed, about half of the sun's energy is reflected. Now, would anybody like to ask any questions about energy getting from the sun to Earth, being absorbed or being reflected? So we need to talk about something called the energy or the radiation budget. Oh, sure. We'll just pause here. All right. So before you try to copy this entire diagram down, I'm going to point out the parts of it that I want you to focus on. The first thing I'm going to mention is this idea of radiation budget. Now, a budget, if you think about money, is where you compare what you make and what you spend, what comes in and what goes out. So a budget is where you're comparing energy that comes in and energy that comes out. And so one thing that I want you to recognize is that the net, that means the overall radiation budget for our entire planet, for Earth, is 0. That means exactly the same amount of energy comes in as what goes out. The difference, however, is that it can be uneven around the Earth. So when we take the Earth as a whole, of course, what comes in and what goes out is the same. But for a specific location, that might not be true. For example, polar regions, the North and the South Pole, or places that are close to them, have a deficit, much like many of our governments have a deficit. It means we are spending more than we are making. So in the sense of energy, it means that more is being reflected than what is being absorbed. Regions near the equator have a surplus. They absorb or they receive a lot of energy, but perhaps less is leaving. But if we take our deficit and our surplus areas and put them together, the overall total is still 0. So there are a couple of things that I want to remind you of that you know. One of them is about the laws of thermodynamics. The first law, we know because we just learned it, says the energy that comes in has to equal the energy that goes out. So if we look at this picture, there's 100%. And notice that it's not all going to the same place. So some of it is reflected right away. Some of it is absorbed. Some of it is used. Some of it is converted into heat. But eventually, if I took all of these numbers up here, I would get all 100% of it back. So we have to account for all of the energy that comes in from the sun. So that's the first law. The second law says that conversions are not 100% efficient. So what you need to recognize is that when the sun's energy comes to our planet, comes in the biosphere, it's going to be converted. And we're going to get heat being produced. And so generally, if I was to sum up what is coming in and what is coming out, light is coming in, heat is what's going out. Because the sun's energy will get absorbed, it'll get converted, heat will be produced. It'll get converted again, more heat will be produced. So eventually, all of that light, all of that electromagnetic radiation will be absorbed or reflected, heat will be produced, and heat is what we radiate back out into space. Now, does anyone want to ask any questions about the laws of thermodynamics here before I talk about the other part? So the net radiation budget is really talking about the laws of thermodynamics. What comes in and what goes out have to be equal overall for the whole planet, but it's not necessarily that way everywhere. Now underneath here is where we make a link between physics and biology a little bit more. So I'll just move this up. What it says is that energy always flows. Energy is not a thing that just sits still and is static. It's constantly moving, it's constantly changing. When we talk about a system, we could be talking about a machine like we were in physics, or we could be talking about a living ecosystem, which is the slant that we're going to take in this unit. So energy is what makes an ecosystem work. Without energy, like we said at the beginning, without the sun, eventually everything's going to die. Now it might be, and this word is temporarily, it got cut off. So it might be temporarily stored and given off later. It might be changed from one form to another. So if we talk about an ecosystem, when a plant performs photosynthesis, it's storing energy in glucose. When an organism eats the plant and then starts running around, it's converting that chemical energy into muscle contractions. But it's never, ever, and this word is lost, never lost. It's always going somewhere. So the idea is that energy flows, and this causes matter to cycle. By matter, we mean things that are made out of atoms. So without energy, photosynthesis and cell respiration would not happen. They are things that are based with matter. Without energy, life would not exist. So the next point is where we're going to talk about a couple of examples of energy conversions that are more biological, that would release heat. A really good example is muscle contraction. So anytime your muscles or any organism's muscles contract, that is a biological process where energy is converted and a bit of heat is produced. Decomposition is another really good example of a biological process where heat is produced. Now I'd like to mention photosynthesis specifically, and I alluded to this on the last page. During photosynthesis, only about 1% of solar energy is actually used for this. So if you think about every living organism and where they're getting their energy from, only about 1% of the sun's energy is actually used for photosynthesis, which becomes the basis for all food chains. So most of the sun's energy is doing something else. So even though we don't need a lot of the sun's energy to have food chains that work and that exist, that one bit that we need is absolutely crucial. So we're going to talk about energy relationships. So the relationship between energy that comes in and energy that goes out, and what affects that. So like I mentioned on the last slide, energy that reaches the Earth's surface is not evenly distributed. But we've got to get energy moving around our whole entire planet for life to exist. Things like cloud cover. So there's my first picture talking about the weather. How many clouds there are on average or on a given day will affect how much solar energy is reaching that particular spot. So if it's a really cloudy day, or there are clouds produced by something else, perhaps clouds that are made up of industrial pollution, perhaps clouds that are from a volcano erupting, even though that might be a natural event, it would still reduce the amount of solar energy that can come in. Latitude would be another one, and that's what my second picture is for. My second picture shows a little diagram, and we're going to talk about these diagrams. They're called a climatogram. They illustrate average conditions for a particular area. And I picked 3 cities that were actually in Alberta: Medicine Hat, Edmonton, and Grand Prairie, to show you that their climate is not the same, and one of the things that causes that is latitude. Medicine Hat is way at the south of our province. Edmonton is sort of in the center, and Grand Prairie is way in the north. They are at different latitudes, and the latitude that you are at has a huge influence on average temperatures and on precipitation. Now the last thing on my list is albedo, and it kind of goes with this idea of cloud cover. Albedo is a term that we'll see that talks just about whether or not something absorbs or reflects. It's not talking about specifically that it's a cloud. So we'll talk about this in the sense of atmosphere, but also in the sense of the lithosphere. But these 3 things influence the amount of solar radiation that part of the Earth receives. And the result is differences in weather and climate. So I figure we better know what climate and weather are. Climate is the prevailing weather conditions of a place determined by a bunch of factors: temperature, precipitation, wind, clouds, sunlight. But the key is that it is over a period of years. Climate is like an average. So when you're watching the news and you hear them say the average high for today is 0 degrees, that's because we've looked back over tens or hundreds of years to see what was the temperature on this day. That's what climate is. Climate is the long-term average. Weather is the conditions at a particular time. So if I was to talk about weather, I would say today it is sunny. That's weather. That's talking about what's happening right here, right now. Not what it's normally like, but what it actually is like right now. Now, would anyone like to ask any questions about any of those ideas so far? What I think we're going to do then is we're going to talk just about latitude today, and we'll talk about some of the other factors that influence energy in the biosphere in our next class. So we're going to talk about latitude. So just looking at the picture that's up here, you can see that the way that the lines are going are different for the three different cities. And a big contributing factor to this is their latitude, so how far away they are from the equator. I'm not going to ask you to know specific latitude numbers, but to be able to compare places if I were to tell you what their latitude is. So your latitude, by definition, is your position on Earth relative to the equator. So I remember learning at some point in my school life that latitude was flatitude. They were the horizontal lines. If you have a globe, you'll see there's lots of little horizontal lines on it. Some of them have names like the Tropic of Cancer, the Tropic of Capricorn. I don't know anything more than that. I think those are the only ones I can list. But the idea is that your latitude is your position relative to the equator. That location determines the angle of incoming solar radiation. And so I'm going to talk about that. Now the picture that we have here is to illustrate the angle of incidence. That's the angle of incoming solar radiation. Now on this picture, we would imagine that our equator is right here. That means that up here, this is a polar region. And those are the words that I'm going to use to describe latitude. Is it polar? Is it equatorial? Or is it somewhere in between? The closer you are to the equator, the more you'll have characteristics similar to cities at the equator. The closer you are to polar regions, the more like that your climate will be. Now, what I'd like for you to see, first of all, is what happens at the equator. You'll notice that it says sun down here. So the sun is shining on our planet. And when the sun shines, it hits the equator sort of head on, directly, vertically. The sun's rays are not coming in on a slant. They're coming in very perpendicularly. And I want you to look at the size of this circle. What we're trying to say is that the sun's energy is distributed over a relatively small area because we're hitting it straight on. Up here, for the polar regions, notice how now the sun's energy is distributed over more of an oval shape. And that's because the more polar you get, well, the Earth is kind of like a sphere, the curvier it gets. The sun's light is not hitting you directly, it's hitting you on an angle. These are called oblique rays. And the idea is that this is a larger area. So the closer you are to a polar region, the less sun each specific area gets because it's spread out over a larger space. So the difference is the light hitting it straight on, or is the light hitting it at an angle? Now you could see this in effect on a sunny day such as this by changing your position and looking at what happens to your shadow. You could make your shadow seem really, really tall, or you can make your shadow seem really, really short, depending on which angle the sun is hitting you at. And that's exactly what's happening here. The result of this is that the amount of light absorbed is different. Polar regions absorb less light because they're getting less. The light is spread out over a larger area, so each specific area gets less. Now, would anyone like to ask any questions about this idea of latitude and angle of incidence? So the other thing that we have to talk about is this idea of seasons. And we are going to talk about the angle of inclination. Now, if we were to look at our planet, or if you have a globe, you might notice that it's tilted. So this bottom picture down here is to illustrate that the North Pole and the South Pole are kind of on an angle. And that's how our planet rotates, on an angle. The angle of inclination is about 23 degrees. That means that if I was to look straight up and straight down, the North Pole is actually 23 degrees away from completely vertical. Now, you wouldn't think that this would cause a big effect. Honestly, 23 degrees is not that much, but it makes a huge difference in terms of seasons. Because of this angle of inclination, for part of the year, the southern hemisphere is closer to the sun. That means that for part of the year, the southern hemisphere is getting more direct sun rays. It's hitting at less of an angle. When this is true, it would be summer in the southern hemisphere. Now, I chose this because that's what's happening right now. Right now, it is summer if you are in the southern hemisphere. And right now, we know that in the northern hemisphere, it's winter. And the opposite would be true when it's summertime here. When it's summertime here, we would be closer to the sun than the southern hemisphere. Now, so that you know, the way that you determine which season you're in, which part of the year you're in, is called a solstice. I'm sure that you've heard of these before. Does anyone know what a solstice is? I heard someone go, solstice, like it was a thing they knew about. So the solstice, and it's actually coming soon, winter solstice, December 21st. This is the shortest day of the year for us. If you're in the southern hemisphere, it's the longest day of the year. There's another solstice that happens in June. That's the summer solstice. For us, it would be the longest day of the year. For the southern hemisphere, it would be the shortest day of the year. Now, if you live in a very polar region, so for example, Inuit populations that live way in the northern part of, say, Nunavut or the Northwest Territories or the Yukon, there's a day in the winter where the sun basically doesn't ever come up. That's the winter solstice. And there's a day in the summer where the sun essentially never goes away. That's the summer solstice. So the effect is magnified the closer you are to a polar region. Now, the picture that I have down here is just to illustrate to you, this would be our summer. If it's our summer, you'll notice that the North Pole is tilted more towards the sun, and that means that the sun's rays are hitting more of the North Pole. And notice down here, the South Pole is not even in the path of the sun. So if you're at one of the poles, that's why the weather is so extreme for part of the year, because you're not in the direct path of the sun. You would only be getting heat that had been transported from around the globe. Does anyone want to ask any questions here about seasons or angles or anything that's on this page? Yeah. In our summer, it's not that it never ever gets dark, but for a lot of days, the sun will only set for a really short amount of time. And on the summer solstice, it basically doesn't. It depends how close you really are to the North Pole. So as you come closer to the equator, the effect is less. But there's a day where the sun doesn't go down. It's like a big party. They have a big festival thing that day. Does anybody else have questions that you'd like to ask?